now that we have a couple of different ways of writing electron configurations or information about electrons within the atom, we're actually going to break up electrons into two categories. And those are, of course, written here, valence electrons and core electrons. Okay, so valence electrons, the definition of valence electrons are the electrons that have the highest N value. Okay, so they're all the way out on the outer edge of the electron, since we know that the higher the N value, the larger the energy and larger the atomic size of that orbital. And these are one of the most important factors for determining the properties of a given element. So it's important that we're going to be able to need to discuss these. Okay, all of the other electrons, the electrons in the lower energy shells, are referred to as core electrons. And the easiest way to figure that out is if you know the number of valence electrons, just subtract that from the total number of electrons. Okay. So let's do a couple. Let's see how many electrons, valence electrons, carbon has. So one of the easiest things to do is just write out its electron configuration, either reduced or full, complete, as we'll see. But we can see that carbon is 1s2, 2s2, 2p2. And so we are going to ask ourselves, what is the highest energy level for carbon? And that is 2, n equals 2. And there are 4 electrons in that highest energy level. So carbon has 4 valence electrons. Okay. What about something like oxygen? Oxygen is 1s2, 2s2, 2p4. So oxygen has 6 valence electrons, 2s2 and 2p4. What about argon? Okay. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. So how many valence electrons does argon have? Well, its highest energy level is 3, n equals 3. It has 2 in 3s, 6 in 3p. So that's a total of 8 valence electrons. Okay. Now it turns out when we introduced the idea of noble gases, such as argon, we said they were really stable or inert elements. And it turns out that both quantum mechanically and just empirical evidence suggests that 8 valence electrons is the reason why they are so inert, so unreactive, and therefore stable. 8 valence electrons seems to be a a region of stability for elements. Okay, except for smaller elements such as helium. Helium and small elements are very stable with 2 valence electrons. But again, this idea that all of the, here we have the reduced, or just the outer highest N value electron configurations for these elements, all of them have 8 valence electrons. All of them are in group 8A. So when you use the A group distinctions, 8A, 1A through 8A for the main group elements, that turns out that that's also going to determine or tell you how many valence electrons they have. It turns out that 8 valence electrons equals a stable electronic configuration. So it turns out that most elements, or a lot of elements, are going to react in a manner to achieve 8 valence electrons. Okay, so here we have all of the group 1 metals. They all have 1 valence electron. And so if they were to lose that 1 valence electron and create a +1 cation, they would have 8 valence electrons. Basically the lower energy electronic configuration. So let's do an example for sodium. So sodium has the electronic configuration of 1s2, 2s2, 2p6. If it loses 3s1, excuse me, if it loses 1 electron to become a sodium +1 cation, its new electron configuration is 1s2, 2s2, 2p6. 8 valence electrons. So by losing that 1 valence electron, it has 1 less electron. It now has 10 electrons rather than 11, and 8 valence electrons becoming more stable. The trend is also observed on the other side of the periodic table, the halogens. They all have 7 valence electrons. So by gaining 1 electron, they become an anion with a -1 charge and, of course, 8 valence electrons. So we take a look at fluorine. We can see that fluorine has a 1s2, 2s2, 2p5 electron configuration. If we take a look at fluoride -1 ion, it has gained 1 electron, so it becomes 1s2, 2s2, 2p6. 8 valence electrons, a more stable species. This is known, the fact that elements will react in a manner to achieve the 8 valence electrons. This is known as the octet rule. Okay, we observed the examples group 1 and group 7A, but it's the same and can be said for a majority or a lot of elements, and we'll look at a table that predicts them. Also, in addition to the octet rule, again trying to get 8 valence electrons, the small elements can be like helium with 2 valence electrons, so that is known as the duet rule. Okay, hydrogen is an example of that. Okay, so here is a table of elements that form predictable ions, and again it depends on how close they are to achieving that octet rule. Group 1A elements will lose 1 electron. Group 2A elements will lose 2 electrons. Aluminum in group 3A can lose 3 valence electrons to get to the 8 octet rule. Halogens can gain 1. Group 6A, the chalcogens, oxygen, can gain 2. Nitrogen and even phosphorus, for the most part, can gain 3 to get to the octet rule. Okay, so this is a must-know concept, the fact that these elements are going to gain or lose electrons to get to the octet rule, and these elements listed here are absolutely predictable in that if you see these ions in a compound, in an ionic compound, they will always have these charges.